Welcome back! This video amplifies on my previous video discussing CH500 series RISC-V software examples. Here we will discuss controlling 3 NEOpixel strips from the CH583 RISC-V microcontroller. The 583 is a small and inexpensive MCU typically priced at less than $1, even in low quantities. As in the previous illustration, we will accomplish this task by harnessing various resources of this MCU beyond just the two SPI interfaces. We will dive into using the DMA on the SPI as well as receiving interrupts when the DMA is complete to signal us to move on to the next strip. So how are we going to control 3 strips with only 2 SPI peripherals available? Glad you asked. My original intent was to manage 4 strips, but the CH583M is missing one of the resources I had hoped to use. The secret is to use the alternate pin configurations available on most of the peripherals to alternately redirect the output of a single SPI to 2 different strips. Unfortunately, the 583 only offers this feature on SPI 0. We will only be able to connect a single strip to SPI 1. I need to mention that the other members of the CH500 family only provide a single SPI interface, so our best choice is to use the 583, and specifically, the M variant, which is the one that brings out all of the signals we need. So, we start by creating a new workspace and project in Moon River, specifying the CH583M as the MCU. Don't worry if you only have a 582 or 592. There are hooks in my source code to set the number of strips to 1, 2, or 3. You will still be able to appreciate the mechanism of running a second strip by switching to the alternate MOSI pin whenever we wish to display the second strip. Speaking of hooks, we can use the chip ID register to set up the configuration automatically. In retrospect, I really should have started this project using C++. We have strip and segment variables used to produce the animations which need to be static across instances of the animation subroutines. Anyway, C++ evolved from the judicious use of structures in C, so this is what we will do in this episode of the project. The main workflow consists of setting up the hardware such as the UART and onboard LED, followed by a custom SPI setup routine. We then proceed to clear all of the strips in reverse order. This is followed by setting up buffers, which I call pseudo-strips. For each of the NEOpixel strips, specifying the length and a background color or pattern. We then need to fill in the struct for each strip, as well as each of 5 possible segments we may wish to use within the strip. Each segment may contain a different animation. This is equivalent to instantiating a C++ class for each strip, and its segments. I include the concept of a sprite, which is a sequence or pattern of pixels which may be made to move within the bounds of a segment. We set up the sprites using the fillSeg routine. We can indicate a single color or a pattern of colors, as well as setting the length in pixels. This done, we enter an infinite loop which will perform the animations we wish to see displayed on the strips. We then call the show function, which sends the contents of each pseudo-strip buffer down the LED strip via the SPI to which it is assigned. Before terminating, the loop increments a master ticker variable. Each animation can change its timing by referring to this ticker. The length of these ticks is controlled by the final delay call in the loop. We also add in a 100 microsecond delay which is required to let the individual strips know that we are finished sending data. There are some technical details used in the show routine that are worth examining. One is the compression algorithm we use to get more performance from the SPIs. We have 2-bit and 3-bit routines. If you have followed some of my earlier blogs, you may be familiar with my use of the term neobits, which are actually 3 bits of data sent via SPI. So it is not at all difficult to fit 2 of these 3-bit neobits into an 8-bit SPI register with room to spare. But how do we get 3 of them into 8 bits? The magic is in the timing used by the LEDs. By definition, there will be a low level between each transmission of the SPI. This means that we do not need to explicitly account for the last bit of the last NEO bit, which will always be low. It will automatically be set to 0 for us. This magic goes up in a puff of smoke when we use the DMA, which does not give us a break between SPI byte transmissions. So we will find both a Compress2 and a Compress3 routine in the source code. Please check the description for the link to my blog, which describes the DMA in greater detail as well as its possible advantages. And just like that, we can upload our code and watch the magic happen. 3 NEOpixel strips, all controlled by a single tiny CH583M RISC-V MCU. Thanks for watching, and happy coding! In the next video, I hope to have a C++ version of this project, as well as adding Bluetooth remote control and more animations. Please leave a comment if you have any ideas about a simple existing Android app for controlling LEDs, preferably using Bluetooth serial and with example source code for using it. Please like and subscribe. You know the routine. Happy risky coding!